Hi everyone, our lesson for today is general solution of non-homogeneous differential equation. In this video, we're going to find the particular integral when capital X equals sine AX or cosine AX. This is the general form of a non-homogeneous linear differential equation with constant coefficients. This is the equation. Now, when capital X or the right side is equal to sine AX or cosine AX, the equation becomes like this. For the general solution, this is our formula. Y equals complementary function or CF plus particular integral or PI. We learned how to solve for CF. So this time, we're going to determine particular integral when capital X equals sine AX or cosine AX. Let's begin with PI of sine AX. This is equal to 1 over f of d squared times sine AX. After that, we're going to have 1 over f of negative a squared times sine AX, which means we're going to replace d squared by the negative of a squared. This is now the PI of sine AX, provided that the denominator is not equal to 0. Now for the PI of cosine AX, the formula is 1 over f of d squared times cosine AX. Then this will be equal to 1 over f of negative a squared times the cosine of AX, which means, again, we replace d squared by negative a squared. This is the formula for the PI of cosine AX. Take note that the denominator must not be equal to 0. For some problems, the denominator equals 0. In that case, we're going to multiply the numerator by x, then differentiate the denominator with respect to d, and again replace d squared by negative a squared. We will continue the same process until the denominator is non-zero. Here is an important note. The operator capital D, that means differentiation concerning x. Now we have this 1 over d. This is called inverse operator, which means integration concerning x. Let us see example 1. Solve the equation second derivative of y with respect to x plus 4y equals cosine 3x. The general solution is y equals CF plus PI. Let's begin with finding CF. Using operators, the equation here can be rewritten as the quantity d squared plus 4 times the variable y equals cosine 3x. Our auxiliary equation becomes m squared plus 4 equals 0. Then we will solve. Let us transpose this positive 4 to the right. It becomes negative 4, and then we square both sides. So m is equal to plus or minus the square root of negative 4. Then we simplify this into plus or minus 2i. The value of m is one pair of complex roots. It means the alpha equals 0 and beta equals 2. We're going to use this formula for the CF. Let us substitute the values of alpha and beta respectively. So the CF now becomes like this. and we simplify our equation further into c sub 1 cosine 2x plus c sub 2 sine 2x. So the CF we will copy in here. Then we go to the next step to find the PI. Our PI of this cosine 3x, the formula is 1 over f of d squared times cosine 3x. Using the operators, we have now this 1 over d squared plus 4 times cosine 3x. Now we replace d squared by negative 3 squared. Take note that our a here is this constant 3. So the negative a squared is negative of 3 squared. And we know that this is negative 9. So the negative 9 we replaced in here. When we simplify the denominator, it becomes 5. So we have negative of 1 over 5 cosine 3x. This is the value of the particular integral. So for the final answer, we are going to add the CF, then the particular integral. It becomes like this. Example 2. Solve the equation second derivative of y with respect to x plus 2 times dy over dx plus 5y equals sine of 2x. The general solution, y equals CF plus PI. Let's begin with finding the CF. Using operators, we write our equation here to be the quantity d squared plus 2d plus 5 multiplied by the variable y equals sine 2x. The auxiliary equation becomes m squared plus 2m plus 5 equals 0. Then let us solve the m using quadratic formula. The value of m will be negative 1 plus or minus 2i. So the values of m would be one pair of complex roots, which means the alpha equals negative 1 and beta equals 2. So we're going to use this equation. When we substitute the corresponding values for alpha and beta respectively, we have this equation for the CF. Let us copy this value somewhere here. Then let us find the PI. For the PI of sine 2x, the formula is 1 over f of d squared times sine 2x. Let us use the operators, and we have the denominator here to be d squared plus 2d plus 5. Then we replace d squared by the negative of 2 squared. Take note, our a here is 2. One more thing, we are going to replace the values of d squared only, not the d. So this negative 2 squared will be negative 4. Substituting that value for the d squared, it will be like this. Then we combine this negative 4 with a 5. We have now this 2d plus 1 in the denominator. In this case, there is a value of d. Next step is we're going to multiply and divide by conjugate. So the denominator here is 2d plus 1. The conjugate is 2d minus 1. We multiply this conjugate in the denominator and in the numerator. In the numerator, it becomes 2d minus 1 over. The denominator becomes the square of 2d minus 1 square. We simplify this 2d squared, and this becomes 4d squared minus 1. In the numerator, we multiply the sine 2x with 2d, also with the negative 1. So it becomes like this. At this point, we're going to replace d squared by negative of 2 squared. And the d squared now becomes negative 4, and we simplify the denominator to be negative 17. In the numerator, Take note that we have this d of sine 2x, which means we're going to take the derivative of sine 2x with respect to x, and that is equal to 2 cosine 2x. Let us substitute this value in here. So that will be multiplied by the constant 2, and we simplify further the numerator into negative of the quantity 4 cosine 2x minus sine 2x, and then the denominator all over 17. This is the value of our pi, and we copy it here. And for the final answer, we just combine the CF plus the pi, and it becomes like this. This is the final answer. Example 3. Solve the equation second derivative of y with respect to x plus 9y equals cosine 3x. The general solution, y equals CF plus pi. Let's begin finding the CF. Let us write the operators into d squared plus 9. The quantity is multiplied by y equals cosine 3x. The auxiliary equation is m squared plus 9 equals 0. Let us solve for m. So we have m squared equals the negative 9. Let us take the square root of both sides. We have m equals plus or minus the square root of negative 9. And we simplify this further into m equals plus or minus 3i. So the values of m are one pair of complex roots, where alpha equals 0 and beta equals 3. We're going to use this formula, and we substitute the values of alpha and beta respectively. And it becomes like this, and we can simplify this further into c sub 1 cosine of 3x plus c sub 2 sine of 3x. Let us copy the value of CF somewhere here. Then let us find the pi. The pi of cosine 3x equals 1 over f of d squared times cosine 3x. Let us use the operators to simplify the denominator. So we have 1 over d squared plus 9 times the cosine 3x. In here, we replace d squared by the negative of a squared. Our a is 3, so we have here 3 squared. So simplifying this, we have negative 9. Then we put the negative 9 for d squared. When we simplify negative 9 plus 9, it becomes 0. 1 over 0 is undefined. In this case, we will go to the next step, and that is to multiply the numerator by x and differentiate the denominator concerning d. We are talking about this equation. So we multiply 1 by x, it becomes x, and then we take the derivative of this function. The derivative of this d squared plus 9 will be 2d. From here, we're going to rearrange in such a way that we will show that this is x over 2 times 1 over d cosine of 3x. Remember that this 1 over t is equal to integral. This is the reverse operator. It means we're going to have x over 2 times the integral of cosine 3x dx. We can simplify this integration into sine 3x all over 3. We can multiply 2 by 3, and we have this 6. This is the value of the pi. We can write that value somewhere here, and for the final answer, we simply combine the CF plus the pi. So this is the final answer. I hope you learned something from this video. See you again next time.